Hey, what's up YouTube? In today's video, I'm going to demo a new blueprint tool I just released on my Patreon, and I also do a quick breakdown and show you how it was built. Now, not so long ago, I released a video in which I showed how to use Blender to bake an NFT water simulation into a tiling, looping flipbook. Then, even more recently, I explained a technique to approximate caustics in real time, which then made me think of this tool I prototyped quite a while ago. It allowed me at the time to generate actual caustics in real time and bake them into a tiling looping flipbook. It was back then really sketchy, but it somewhat worked as a proof of concept, and so I finally decided to revive it, and here it is. The thing is, this sort of caustic tool already exists in Unreal Engine. It's a bit hidden away, but if you enable this plugin, you should have access to a blueprint tool that does just that. Now, I used a different approach for my own tool. This one spawns a huge amount of photons using static mesh instances on C++, I think, and I personally chose to rely on Niagara to do something really similar, and I'll explain how it works in a minute. It's not necessarily a better approach, just different, and different is good. Lets you experiment with new methods and potentially discover new things. But then I thought it'd be pretty disappointing to release a tool that is just a copy of something that already exists, right? So why not put some extra effort in and turn what was first meant to be just a caustic flipbook baking tool into a generic water flipbook baking tool. One that would not only allow me to bake caustics, but also very easily let me bake wave offsets, normals, foam and more, kinda like I showed in that FFT flipbook video, but this time in engine. And I think I succeeded in some parts and failed in others. It's far from perfect, but still I reckon it could be an interesting tool to have around, because within a couple of clicks you can very easily build that kind of water shader, which looks decent, not so much up close, and that's the main issue, but oh well. It also may not look as great as that FFT water simulation baked in Blender, because well, this tool doesn't bake an NFT simulation, because it's quite complex to set up, so for now I rely on good old Gerstner waves, and so the result doesn't look as sharp and realistic as an NFT simulation. However, because this is an offline tool, you can go nuts with the waves count and not worry about performance, and you can get a somewhat decent result still. That being said, I also realized the huge benefit of an NFT simulation isn't just in the way it efficiently computes tons of waves, but also the way it computes a believable wave spectrum based on a complex mathematical model. And sadly, you are not going to have a similar look with Gerstner waves, which parameters are just naively lerped between min and max values, right? Plus, the more waves you add, the trickier it is to handle the increasing horizontal displacement. Very quickly you get waves looping on themselves, and again here an NFT simulation handles this issue much better. Although that flipbook tool still suffers from the same issues I mentioned in that FFT flipbook video, namely it's not super high res because I do have to bake quite a few frames to have a smooth animation, and thus I'm kinda limited in resolution even with 4K flipbooks. And 4K flipbooks are not lightweight. It's not necessarily huge by today's standards, but it's still a consequent memory budget you have to account for. The resulting water shader also requires a few texture samplers, but then I consider this to still be somewhat cheap, and there's probably ways to optimize this anyway. Those flipbooks also tiles both in space and in time, so that may be noticeable for sure, especially if you zoom out far enough. All in all, if you have the knowledge to build an NFT simulation in engine, probably best to do so, but then the simplicity of such tool is kinda nice as well, so I'll let you be the judge of how useful it may be. Plus, there's really nothing preventing you from improving upon that tool and using an NFT simulation to bake offsets, normals and so on, the same way I currently do using Gerstner waves, right? You'd get a much nicer looking water, so there's room for improvements for sure, but for our first version, Gerstner waves will have to do. Anyway, enough talking, time for a quick demo. Alright, it's actually really straightforward to use. Right click on that widget here and click Run. You're prompted with a few panels you can open and close. The first one is used to fine-tune the Gerstner waves parameters. So you can mess around with the number of waves, amplitude, length, steepness and so on. That's all pretty straightforward. This parameter might, however, be confusing, but honestly you shouldn't really have to tweak it, and I'll have a better chance at explaining what this does during the breakdown later on. There are the wave presets here, but it's a bit limited, meaning that you cannot add or remove any through that interface. They are for now hard-coded in the widget blueprint, so you can add your own, I guess, but you have to do it manually in that blueprint. It's actually a feature I built in last minute, just in case it proves useful, but making it user-friendly would probably require way more time and effort than I'm willing to spend, given that I spent enough on that tool already. So I'm not sure I could do things differently anyway. This being a blueprint-only tool, you do eventually reach limitations as to what you can do with assets in editor. Anyway, assuming that you've tweaked those wave settings to your likings, you may then switch to the Capture tab and decide, well, what kind of wave data to capture into a flipbook. And so at this point, you may want to preview what's captured. Although if for any reason this is a bit much for your hardware, you can turn real-time preview off, which should help with performance, and manually refresh that view when needed. Moving on, you may choose to render the caustics generated by those waves, right? So you can first tweak how many photons to spawn in X and Y, the more the better usually. How many extra photons to add on each side, that's to ensure caustics properly tile, because a photon here may be displaced and end up inside the texture, so that would leave a gap here, so enough extra photons outside this frame have to be generated to ensure proper tiling. You kinda have to eyeball this value. Unfortunately, I wish I had found a way to do things differently, but for now that's how it is. Then you can change the photon size. Too small and you may start to see individual photons, too large and the brightness kinda explodes and it gets kinda blurry, so there's a sweet spot to find based on the resolution and the amount of photons. Displacement is how much photons are displaced by the water surface before being refracted, so the effect is quite subtle, but it's there. Distance is basically the water depth. The more distant the water bed is below the water surface, the more quote-unquote time a photon has to diverge, and so it results in a stronger caustic pattern. Chromatic, that's how much red and blue light frequencies are shifted when refracted, and so red and blue photons don't perfectly line up with the green photon, and this creates that chromatic aberration look, right? This is somewhat a cheat though, too much of a chromatic aberration and you may start to see the individual red, green and blue photons, so best to keep this value somewhat reasonable. Spread is a trick to reduce the wave normals and thus weaken the caustic pattern. It's likely that whatever waves you have configured there will by default create way too strong of a caustic pattern, so you may cheat and reduce that photon divergence by quite the amount until you reach the desired look. Stretch is how much a photon is stretched towards the refracted light direction, so each photon isn't a circle anymore but an ellipse. This may help smooth the overall look and bringing some extra chromatic aberration. This is not physically based and adding too much is not advised. Energy is, well, how bright a photon is. Then you have some post-process settings here. Gamma, fall-off, contrast, it's all pretty straightforward. Last option, you can override the caustic source. By default, they are generated by those Gerstner waves, right? But you may choose to override the source and use, say, an existing flipbook. This is in case you followed my FFT flipbook video and want to stick with this FFT method and just need to create caustics that match your own existing flipbook. Now, height isn't actually required, but you may provide one. Please note, however, that you'll need to use a 16-bit normal map flipbook, so that's a bit of a constraint, unfortunately. Seems like an 8-bit normal map hasn't enough precision for the caustic refraction to behave properly, it just explodes. You can also bake a static caustic texture if you so desire. Same principle here, height isn't actually required, but you may provide one, and again normal map needs to be 16 bits. Those two textures don't even need to tile, because that softness parameter can be increased to create a caustic pattern that tiles. Moving on, you can choose to bake the waves offsets. That's like the XYZ displacement map, okay? Not allowed to customize here. You can select a specific channel if needed. Might be interesting to bake the displacement just in Z if ever needed, who knows. More importantly, you can normalize offsets, because right now those values are both positive and negative, and greatly exceed a -to 1 range. And so normalization ensures values are brought back to a 0 to 1 range. This way you can use an 8-bit flipbook texture which will save up quite a bit of memory, but you'll lose quite a bit of precision. Arguably though, offsets don't need to be super precise, so 8 bits is fine. You'll also need to denormalize offsets in shaders using the normalization value this tool outputs upon bake completion in the logs panel here, and the following formula, nothing too complicated. You may also get that normalization info at a later date by checking the generated assets metadata. Moving on, you can also bake velocities if ever you need that, and those can also be normalized. At first I was really hoping to use this normalized velocity flipbook as a flow map to way more smoothly interpolate all other flipbooks, but turns out that's not the correct approach. I'll probably do a follow-up video on why is that and a potential workaround. It's still a work in progress though, it's complicated. Anyway, you can also bake normals and tweak the strength. A height map can be baked as well, which can also be normalized. Note that this height value isn't the same as the offset in Z. That offset in Z is the wave height before the offset in X and Y is applied, and this height value is the wave height after the offset in X and Y is applied, and both have their own use. I'll let you have a look at my Gerstner waves video if this doesn't make any sense. Okay, last mode, you can bake foam. You may tweak the threshold, this tells how quote-unquote easy it is for waves to generate foam. That's an overall foam multiplier, and fall-off and contrast are both pretty straightforward as well. Note that this foam is persistent, meaning it's up to you to choose how fast it decays using this decay rate. Same with diffusion, this applies a blur path to the previous foam state and lets you have, well, diffusing foam. There are also 2 extra parameters that are kinda a cheat. I wish I had found a better solution, but anyway, the default values seem to work just fine, so hopefully you shouldn't have to tweak these, and I'll have a way better chance at explaining what they do during the breakdown, so for now don't mind these. Okay, so once you have chosen the capture mode, you may switch to the bake panel. Here you may specify the flipbook duration in seconds, that's how much time will elapse between the first and last frame. The amount of frames to bake in X and Y, obviously the longer the duration, the more frames you should in theory need to have to maintain a somewhat coherent and smooth motion. You won't be able to bake 4 seconds worth of animation in just 4 frames, you know what I mean. And here's the resolution of a single tile. So the flipbook overall resolution is that value multiplied by both X and Y, so be cautious here. And finally, here's the amount of pixels to oversample for each frame, and I'll let you watch my FFT flipbook video to know what this is and why is this required. 4 pixels are usually enough. Then press bake and let the tool do its thing. Once completed, you may choose how to preview the resulting flipbook. This is the entire flipbook texture as is, and you may turn on grid to better see those flipbook frames. Or you can choose to preview the flipbook played back at a given frame rate. It's styled just enough to let you double check that it's indeed seamless, and you should really always double check that, especially when baking caustics. Caustics may actually not properly tile if there's not enough oversampled photons. Also down there you have a timeline to double check that the flipbook indeed also loops in time. Then, if you're pleased with the resulting flipbook, you may create an asset given an asset name. Note that it will be prefixed with a number of frames in X and Y and suffixed based on the capture mode. Last feature, just in case you have settings that you really like or settings that you may want to share with your coworkers or whatever, you may click on Get Options. Then copy-paste this in a text file, send it to your coworker, and that coworker of yours should be able to paste those options, click Apply, and the tool should be set up exactly the same way you had it set up. Nice. And that's pretty much it. So let's assume I want to create a complete flipbook state. First, let's bake offsets, and I'm going to choose normalize here, because really 8 bits does a good enough job and it creates a much more lightweight flipbook. Press bake, wait for it to complete, then create the flipbook asset. Cool, then bake normals and create an asset. Then bake foam, which may take a tiny bit longer because it needs a prepass for the diffusion and decay rates to do their thing. Now caustics, let's crank up the photons count to 1k, keep a size of 4 and reduce the energy by quite the amount. Okay, that looks great, press bake. Last one, normalized velocities. I'll personally be using that flipbook for particle effects, so this one can actually be at a much lower resolution. And voila, I end up with 5 flipbooks in this directory. All I got to do now is to create a simple water shader. Use the single layer water shader model, configure it however I like. Then I'm going to use the material function I provided with this tool to sample those flipbooks. Configure those 4 values the exact same way I had them set up in the tool, and if I don't remember that, right click on one of these flipbooks and show its metadata, and it's all there. So 512 pixels, 4 pixels, 8 frames in X and 8 frames in Y. I'm then going to use world position before offsets are applied as texture coordinates, then configure the projection scale and frame rate. Cool, now let's plug in the normal flipbook, now the offset flipbook, and because this one is processed in the vertex shader, this derivative option must be set to false. Then I may reuse the offset flipbook and mask its Z component to get the normalized wave height and bring in some color at the tips of those waves. And to do that I also need to make the water a tiny bit more opaque for the color to kick in. Sweet, now add the foam flipbook, which is going to max out the opacity and bring in some white color. And that's pretty much it for a very basic example. Now you may notice that the resolution isn't great, and that's obviously because in the end each flipbook frame is only 512 by 512 pixels, and so that's quite low res. So one thing you can do to improve this is to sample those flipbooks a second time at a much lower scale and add extra details, kinda like detailed texturing, right? So that's what I did here in this more advanced example. Foam is sampled a second time here at a much lower scale, dimmed a little and mixed with the main foam to perform a hide blend using a static foam texture. The normal flipbook is also sampled a second time and I also blend a static texture, which is going to be distorted by those waves anyway, so it actually doesn't look that static, and it's really just to add extra details at a small scale. And then I further blend those single layer water shader parameters with the wave height to fine tune the look, and that's pretty much it. So you could use this material as a base, make new flipbooks in just a couple of clicks, update them here and have another water shader in a couple of seconds. Then add some particle effects on top and actually make use of that caustic flipbook in the landscape or waterbed material, and voila, you get yourself a decent looking water. Again, it's not perfect and you might not like that baked flipbook approach, I can understand, and in the end I'm not sure I'm a huge fan of that method, to be honest. It certainly has quite a few limitations, so you might prefer a fully procedural approach like an NFT simulation, but then this tool, despite its flaws, allows you to get a nice result with a couple of clicks, and it's quite cheap overall, so as usual, some pros, some cons. Use your best judgment to see if that method fits your needs, and yeah, that's pretty much it. Time to get technical and see how that tool was built. Alright, it all begins with an editor utility widget. This is just like a regular widget blueprint, but one that can be called in editor, and so that lets me have a tick in editor amongst other things. Then there are 2 widgets that are of great help when building utility widgets. The first one is a single property view widget, and the second one is a details view widget. Both pretty much do the same thing. So let's pretend I want to expose some settings in this interface, like say change a float or a boolean. Well, first of all create those variables, names are important. For now, float param and bool param will do just fine. Then let's add 2 single property views. The first one will be bound to that float param variable, and the second one to that bool param variable. Now, I still have to tell those single property view widgets where to quote-unquote find those variables, and that is done using this setObject function. And here I can just send self, because well, those 2 variables are indeed part of this blueprint itself. And the preconstruct event is a great place to call that setObject function. Preconstruct is pretty much just like construct, except that it also triggers when the widget is constructed in editor. Sweet, now let's change that float's default value and maybe set a min and a max range as well. And there you go. I may then listen to their own property changed event, so that when this float is updated via this single property view widget, do something, and when this bool is updated as well, do something else. Sweet, now I could also create a blueprint enum and say have an option A and B. Change that boolean variable to this enum type I just created, recompile, and voila. Then upon option A or B being selected, do this or that, right? Cool, so that's the single property view. Now the difference with the details view is that the details view can do all that automatically for a list of variables in a given category. So let's create a category named, say, parameters. Now I still need to call that setObject function for that one details view widget, and that's it. It automatically creates this collapsible panel with my two variables, and I can also listen to its own property changed event. The only difference is that I now probably need to create a name switch to figure out which property got changed to do this or that, right? Overall, I personally tend to rely on categories nested into categories a lot, and I found that details view doesn't cope too well with that. A single property view widget also allows me to override its variable name, and I like that a lot. And then I find that it's much easier to handle a list of on-property changed events coming from many single property view widgets rather than a single details view widget's on-property changed event that I further have to split using a name switch. And so that led me to prefer using single property view widgets despite having to call that setObject function for every single one of them, but you do you really. They both have their pros and cons, and by the way, shout out to Ryan for making me discover this detail view widget. Anyway, as you can see, I have a lot of these single property view widgets, and this is just for the caustic panel, and so for the vast majority of these on-property changed events, I just forward the updated value, whether it's a float, integer or boolean, to a material parameter collection, or a Niagara parameter collection, or both, but more on that in a second. Alright, so all in all, on the widget side there's not much to say. I have a bunch of single property view widgets, and the rest is quite basic. A bunch of vertical and horizontal boxes, some overlays and some images and text, and that's it. Now, the second order of business is to spawn a blueprint actor that owns all the necessary components for this widget. That one here. This is an empty blueprint. See, it has no logic. It's just here to own components, because a widget can't own, say, a scene capture component, right? So during this utility widgets construct event, I first check if this actor reference is valid, which isn't at first, and so then check if such actor blueprint already exists in the scene, who knows. If one exists, well, there's no point in creating one, so I might as well use it. However, if none exists, create one, and also keep in mind if it has been created or not. If it has, well, I better make sure to not leave garbage behind and delete it when this tool is closed. So, during its deconstruct event, called when the widget is closed, if that blueprint actor was indeed created just for that tool, well, destroy it. And you can see that in action here. If you take a look at this outliner, you can see that actor being spawned when I open that utility widget and destroyed when I close it. Cool. Now again, this actor owns all components this editor utility widget requires. There's a Niagara system for the caustics and a scene capture component to capture that Niagara system. There are also 3 Niagara systems used for readbacks, more on that later on. There's also a subdivided plane, which has a material used to preview the Gerstner waves. And finally, that actor also has a scene capture component used to capture whatever is child of this scene component. That's what creates this preview window, essentially. Note that these components are all set to be visible to scene captures only. So, in this utility widget, once I get a reference to that newly created actor, I then first configure the scene capture components. One is used for the preview window here, so I set its location and rotation here, and its FOV and other parameters here. Then I update its show-only list, so this scene capture component only renders what's a child of this scene, so this light and this subdivided plane. The second scene capture component is the one needed to capture the caustics from a top-down orthographic view, so its location and rotation are set here, and then it's further configured here. Nothing too fancy. Again, I rely on its show-only component list to only render that Niagara particle system. Cool. Once that's done, here I configure the readback emitters, but I'll come back to those later on. Okay, next I check that all necessary render targets are created. First one is the capture render target. That render target contains what's to be rendered on the flipbook, it's what's previewed here, right? Once created, I notify the scene capture component meant to render the caustics from a top-down orthographic view to render into it. Next, I may need a buffer for that capture render target, so it's really just a copy, same size, same format. It will be relevant later on. Then the flipbook itself. Now here I used to create one as well. The thing is, it proved to be troublesome when I wanted to create a static asset from it. It just ceased to work. So for now, I had to rely on an existing render target, which is no big deal really. I can resize it if needed, so it's all good. Next, I also need to create a buffer for that flipbook, again just a copy, so same size and same format. Then here I create two material instances. One is used to composite the render target into the flipbook render target, and I'll explain in details how it works in a second. And the second one is used to just copy a render target into a given buffer. And finally, I also create a render target for the scene capture component meant to, well, capture the preview window. Okay, so that's quite a lot of information already. Let's take a step back for just a second and briefly summarize. This utility widget relies on a blueprint actor to have access to components like scene capture components and such. The scene capture components are configured to only render what they are meant to render, and they do that in render targets created by that utility widget. That widget then has a simple image widget which makes use of a very simple material with a single texture parameter. Texture parameter updated here so that image displays the desired render target. And that's how that Gerstner waves preview window is created in a nutshell. Now, speaking of Gerstner waves, I won't go into too much details here, because I already made a lengthy video on the subject, and a project containing everything you should know about Gerstner waves is also available as a tier 2 reward on my Patreon. Just know that I have a custom HLSL node that generates Gerstner waves with a for loop to support a variable amount of waves and based on a number of parameters. Parameters that all come from a material parameter collection updated in that utility widget here when those single property view widgets are updated by the user. As simple as that. Now that HLSL function outputs the Gerstner waves XYZ displacement and waves normal, and so if I can displace a subdivided plane and preview those waves in that window, I can also, well, use an emissive material to draw that displacement directly in what I call the capture render target, right? And so if the user wants to preview what's captured, that image widget material brush is updated so that its texture parameter points to that capture render target. And then on tick, if that utility widget isn't actually in the process of baking a flipbook, I just update the time value and then draw that material in this capture render target every single frame, and that creates this real-time capture preview window. So for offsets, I just output the Gerstner waves displacement. For normals, well, normals. For velocity, I just compute the difference between the Gerstner waves displacement at a given time and that displacement ever so slightly ahead of time. For foam, I compute the Jacobian of that displacement. More info on this can be found in Desray's blog post here. I'll have it linked in the video description below. And for caustics, well, here I have to rely on a Niagara particle system, as I'll explain in a minute, so I actually need to rely on a scene capture component to, well, capture that Niagara particle system, okay? Hopefully it all makes sense so far. Now let's take a side step for just a second. Again, that utility widget has a ton of single property view widgets, right? And some of them are used to update a material parameter collection, some of them a Niagara parameter collection, some of them both. For instance, anything that has to do with photons is only really relevant to the Niagara system used to create caustics, and so I only update a Niagara parameter collection, which then can be very easily referenced in that Niagara system. Now, it's worth noting that there's a way to link a Niagara parameter collection to a material parameter collection, like so. Upon doing so, this Niagara parameter collection creates all the required parameters to create a perfect duplicate of that material parameter collection. Then you may just update the material parameter collection, and the Niagara one will automatically update as well. Neat. However, that technique has its downsides as well, especially if you're constantly iterating on that material parameter collection, adding new parameters, removing ones. This linked Niagara parameter collection behaves a bit funky, I think. It doesn't necessarily remove duplicated parameters and all, so I'm personally not a fan. Plus, a Niagara parameter collection handles way more variables than the floats and vec4s a material parameter collection can. Niagara can handle booleans, vec2 and so many more, and so that's kinda cool to have. And so I personally prefer to have a material parameter collection and a separate Niagara parameter collection. They both share a few variables, so I do have to update both in some cases, but that's a downside I'm willing to live with, so again, you do you. Moving on, I should also mention widget switchers, because they are great. They very easily allow me to create menus and pages, because a widget switcher may only show one of its children at a time. And so I can choose to display that child widget or that one just by updating its active widget, right? And that's what happens when, say, the capture mode here is changed by the user. I merely change a widget switcher index, and that lets me change menus. Now let's talk about the actual bake process, which is started when that button is pressed. This start capture function looks complicated, but really it just ensures everything is properly initiated and that everything is reset to 0 and ready to go. Going over every single function would take way too long, and this video is already long enough, so sorry not sorry, I'll keep it somewhat short and be quite brief. And really the main takeaway here is that boolean set to true, which makes the tick function take that path here. Each tick, I first compute a custom time value based on the flipbook duration, number of frames to bake, and the number of frames baked so far. So it starts at 0 and ends at whatever duration the user set in seconds, so 2, 3, 4, whatever, and that's the actual time in seconds used to compute the Gerstner waves. Then the time blend value is almost identical except that it's in a 0 to 1 range. I also send the frame offset in x and y to that material parameter collection, which is 0, 0 at first, more on this in a second. Then refresh the capture render target, which is that function once again used to draw material in that capture render target, right? So far so good. Now at that point I want to composite that capture render target into the flipbook render target. Remember, this is an iterative process. It happens on tick over multiple frames to bake and composite one flipbook frame at a time. So I do need to read from that flipbook render target, because it may contain frames baked so far, but I also want to write a new frame into it, and that's a typical read and write conflict. The solution, and it's quite a common thing to do with render targets really, is to first copy that flipbook into a buffer. That way you can read from that buffer instead and write into the flipbook render target without any conflict. And so that's what I do here using this simple material. Which texture parameter is updated to sample the flipbook render target, and it's written into that buffer render target of matching size and format. Then this composite material, which texture parameter is updated to sample that buffer render target, comes into play. What does it do? Well, let's see. First, it samples that buffer flipbook, which again may contain frames baked so far. Then, using a very simple box mask derived from the amount of frames in x and y and positioned based on the current frame offset in x and y, replace whatever was on that flipbook at that frame, supposedly nothing, with that capture render target. Now if the capture mode is 0, meaning caustics are what's baked, I may apply the caustics post-process settings, gamma, fall-off and contrast. The only remaining and important detail lies in the UVs, which are first multiplied to make this capture tile according to the amount of frames in x and y in the flipbook, right? But it's also ever so slightly scaled down to account for the amount of pixels to oversample. This is needed for this flipbook to tile without having bleeding artifacts on the edges, and I'll refer you to my FFT flipbook video if this sounds confusing. So that material is written into the flipbook render target, then I just increment a counter to keep track of how many frames were baked so far, and I also increment a frame offset in x. If it exceeds the amount of frames to bake in x, then reset it to 0 and go down one row by incrementing a frame offset in y. And if that offset exceeds the amount of frames to bake in y, well, I've reached the end of the flipbook and the bake is complete. Well, almost. I do use some sort of pass system, which turns out is only used for the foam to perform a full bake before the actual bake, so the foam can have time to quote-unquote warm up and be diffused first and reach some sort of equilibrium before the actual bake takes place. Which makes me think I didn't explain how that diffusing foam works. It's quite straightforward, and again the method is quite common. First, copy the capture render target into a buffer, assuming that at first there's nothing in it, it's just black, okay? Then write that foam material into the capture render target and rinse and repeat. Next iteration, that capture render target now contains foam previously captured, right? Which is copied again into that buffer. And that buffer is sampled in that foam material to mix the newly computed foam with the previous foam, possibly blurred by some amount, using a simple cubic blur. And based on how much that previous foam is added, you get foam decaying at a varying rate. Sweet. One other important feature I should explain is how the normalization process works. Again, here the idea is to bring positive and negative values, all possibly greatly exceeding a -1 range, and thus needing at least a 16 bits per channel texture, to a 0 to 1 range, so they may fit in an 8 bits per channel texture. So once a bake is completed, I check if I should move into a normalization pass, which essentially enables one of those readback Niagara emitters, which goal is to scan every single pixel on that flipbook and retrieve the absolute maximum value, and while that happens, this blueprint merely waits. So that readback Niagara system is previously configured here to update its texture parameter to point to the flipbook render target. That same system also has an object parameter, which is updated here to set it to self. Having done that, I can then make this utility widget implement that Niagara readback interface, which allows me to create this event. In Niagara, I then add this exporter module, and I first make sure to specify that object variable here, that way Niagara knows with which blueprint to dialog. Then, if that boolean here is true, those two vectors and that float are sent to the utility widget blueprint via this interface event. And if that sounds way too confusing, don't worry, I have a video dedicated to the Niagara exporter interface coming up very soon. Anyway, when the normalization process begins, that boolean is set to true, and that Niagara system is reinitialized, which spawns a new single particle. Then, during update, I have that custom HLSL node that simply performs a single unique texture sample for every single pixel to find the absolute maximum value. Well, it's not exactly true, because a 4K flipbook would mean a 4K for loop within a 4K for loop with a texture sample for every single iteration, which, let's be honest, is a super naive and extremely costly approach, so my GPU chugged quite a bit. So to make this process a little bit less laggy, I spread the workload over multiple frames, and so I only scan a couple of 4K lines at a time, right? And when I reach the bottom, the last line, that progression value I send back to the utility widget along with the maximum value reaches 1, and so that tells me the normalization process is done. At this point, I normalize the flipbook using that maximum absolute value on a very simple material that lets me remap values to a 0 to 1 range. Now again, that's a bit troublesome as well, because I need to both read and write into that flipbook render target, so same trick here, copy it into a buffer and read from that buffer instead, right? And that's how the offset, velocity and height flipbooks are normalized in a nutshell. Once the bake is entirely completed, the user may create a static asset from the flipbook render target, which is done just by simply calling this function. It can be quite finicky, it doesn't work with most render target formats, but besides that, there's not much to say about it. One last thing, I also update that newly created asset to include metadata to store important bake information in that asset file. Sweet. Okay, we are making good progress, almost done. But there's an elephant in the room. Now, I briefly mentioned that I generate Gerstner waves with this HLSL code, right? But I didn't explain how it's made to both tile and loop on and on. Which was a nightmare to figure out. Not because it's complex, because it's actually not, but because the naive approach I ended up using led to complications that I tried to get rid of with no success. But one thing at a time. First, let's see how it's made to loop, and it's actually quite straightforward. Let's say I want to bake 2 seconds worth of animation in my flipbook. The trick is to actually render double that duration and have the second half of the animation overlap the first. Then fade out that animation layer, we may say, and fade in that one. Voila, the animation loops. And that's why I have 2 HLSL nodes in this material function, right? One actually samples waves, one flipbook duration ahead. And the 2 layers are layered based on the 0 to 1 time blend value I mentioned earlier. There's an issue with this method though, which is you get some sort of weird blend of waves while this animation layer transitions with that one, which is especially troublesome with Gerstner waves, because well, some waves simply cancel each other, so you get an overall reduced wave amplitude and wave steepness when that animation blend happens. And I couldn't figure out a smart way to improve this. I tried many solutions, like overlay some animated noise on top to create a much more intricate blend pattern, but it was a dead end. And that issue is actually quite noticeable. Here, have a look at this normalized offset flipbook and take note of the reduced contrast around the middle frames. Or here, with this normalized height flipbook, which is way more contrasted at the first and last few frames, right? Now, it isn't too big of a concern except for foam. Have a look at that foam flipbook and notice how it's much darker around the middle frames. To fix this issue, I actually cheat and boost the wave offsets around the middle frames to account for that averaged wave amplitude, and that's what this value is for. A nasty trick, but it seems to do the job. What about tiling Gerstner waves? Well, let's pretend this is my capture area and this is my Gerstner waves offset map, which for now doesn't tile. Now, if I zoom out a bit, that offset continues on and on, right? So to have the texture tile, the idea is to have that bit here over there. So the trick is to sample the Gerstner waves once in place, then once, but shifted one entire tile in X. Then blend the two with a gradient map, and voila, it tiles in X. Repeat for the y-axis, and you get tiling Gerstner waves. However, same issue here, there's a mix of two wave signal, that time not in time, but in space, at that location where that blend occurs, right? And how large of a blend to compute is actually what this value controls. 1 means this blend occurs across the entire tile, and so you do get average waves all the way across the texture. 0.1 means this blend occurs across 1/10 of a tile, so just around those two edges here, which looks like enough. But it still proved to be troublesome for foam, see? And once again here I cheat and boost the wave signal where that blend occurs, which is again a nasty trick, but it seems to work well enough. Now it's my understanding that you can have tiling Gerstner waves just by constraining the wave's length to, I think, multiples of that tile width, but I had the gut feeling that it was quite limiting artistically, so I didn't try that approach. Maybe I was wrong not trying it, but anyway. Last chapter in that in-depth breakdown concerns the caustic particle system. How is it built? Well, believe it or not, it's quite straightforward and it shares much similarities with that fake caustic method I mentioned in a recent video, at least in principle. First, spawn a large amount of particles in a grid, and let's pretend those particles are photons, light particles, right? Then have them match the water surface. Now I'm not going into too much details here, because this video is really not meant to be a Niagara tutorial, but anything done in materials can be done in Niagara the exact same way, using GPU emitters, right? HLSL code can pretty much be copy and pasted, and so I generate Gerstner waves in Niagara the exact same way I do in materials, and so that let me position photons on the water surface, right? And also know the wave slope. Then those photons still have to travel underwater, and so at this point, given a light direction, the wave slope and the water refraction index, 0.75, I can very simply compute the refraction vector using this simple HLSL function. And so I get the refracted light vector, and finding a photon's end position is then just a matter of doing a simple line-to-plane intersection test with a flat water bed at an arbitrary depth, and Niagara already has a function to perform such line-to-plane intersection test. Neat. The resulting position is then what I call the caustic position, which is output by this custom module. That module is then duplicated 2 more times, and so I end up with 3 caustic positions. Why 3? Well, I actually went with quite a naive approach to create a chromatic aberration effect. I just stack a red, green and blue photon on top of each other. Then for the red photon, I slightly decrease the water refraction index, and I slightly increase it for the blue photon, and that gives me 3 slightly different caustic positions. Positions that are then used to draw 3 photons using 3 different sprite emitters, one blue, one green, one red, and based on how much they overlap and using an additive material, you get white caustics with some variable amount of chromatic aberration. And you know what? That's really pretty much it. Now I do compute some extra logic in that module to stretch photons in a given direction and whatnot, but it's icing on the cake really, and not required at all to build the core of that caustic effect. Now, assuming that the waves used to generate caustics tile, you do end up with a tiling caustic pattern. The only issue is that, well, Gerstner waves offset photons in X and Y when matching the water surface, and those photons are also further offset in X and Y once refracted. So say that photon here may end up way within the texture, creating a lack of photons in that area. And I spent an absurd amount of time trying to elegantly handle this issue, like say shift those photons one entire tile in X, but for some reason I couldn't figure out how to handle the one line and row of duplicated photons that you do require. Because let's assume photons are not refracted at all, that photon right here is actually the same as that one, right? This texture is supposed to tile, so this bit here is that photon's left side, and this bit here is its right side. So you do need 2 particles for 1 photon, but not necessarily for those photons, so I don't know, it made my brain go kaboom, and so I went for a much easier solution, which is to spawn enough extra photons outside the capture area to fill any gap. And that I think concludes this breakdown video. Hopefully I gave away enough information and explained enough of these tools' inner workings so that you now have a good grasp on how it works and you can start building your own if you're interested in doing so. You're also more than welcome to join my Patreon if you want to get your hands on these project files, which are available as a Tier 3 reward. You also get access to quite a few other projects as well, so feel free to check it out. Thanks once again to all my Patreon supporters. I wouldn't do this kind of projects and videos without you, so I appreciate you all. That's it for today's video. I hope you liked it. If you did, feel free to leave a like and subscribe to the channel. I'll see you in the next video. Take care of yourself. Bye bye!